Hello and welcome to the lectures on state space approach to control system analysis and design. We are discussing the design of controllers based on multi-rate sampling, and we derived in the last lecture an important relationship between the multi-rate samples of output, the system state and the input. Now in this lecture actually we will be concentrating on design of the multi-rate output controller, which will be equivalent to a state feedback. So we proceed ahead and just we will have in next few slides a recap of important points from the previous lecture. So we considered a continuous linear time invariant system of order n with m inputs and p outputs. This system we discretized at the rate 1 by t0 on the input side and at the rate n1 by t0 for output 1, n2 by t0 for output 2, n3 by t0 for output 3 and so on, np by t0 for output p, pth output, and this n1, n2, n3, etc. these are integers. So when we did that, we obtained this relation between the system state, the stack of outputs and the inputs to the system. And here C is n bar by n matrix, bold gamma is n bar by m matrix, and this stack of outputs y is a n bar vector. And then this n bar is summation of all these n. This we saw in the preceding lecture. And we saw these expressions for the matrices bold C, bold gamma and bold y. So recall, this part is n1 rows coming from the corresponding to the sampling of output 1. This part n2 rows corresponding to the sampling of output 2, and this last one is the part corresponding to the np samples of pth output. Similarly, in the gamma matrix, this part corresponds to the first output, this part for second output, and this part for last pth output. This first n1 samples are samples of output 1, next n2 samples are samples of output 2, and so on. Last np samples are samples of pth output, and of course this n1 plus n2 plus etc. up to np we denoted by n bar. We proceed further. We mentioned these two important characteristics. First thing is that rank C will be n subject to this condition, that n1 is greater than the observability index of output 1, n2 greater than the observability index of output 2, and so on for all the p outputs. And also the rank of this augmented matrix C gamma, both bold ones, bold C, bold gamma, will be sum of the system order and the number of inputs subject to these conditions. These we saw in the previous lecture. Now with that background, we are ready to discuss the multi-rate output controller and how it is equivalent to a state feedback. So like in the Leuenberger observer, we introduced a dynamic system, the observer wale dynamic system. Similarly, the multi-rate output controller is also a discrete time dynamical system of order n, given by this equation. The input at k plus 1th instant, sampling instant, is expressed in terms of the input at the kth instant, sampling instant, kth sampling instant, and the feedback of the stack of outputs which we introduced in the last lecture, or we recalled a little while back. So multi-rate output controller has this structure. It is of order M and it is a discrete time dynamical system. This is the starting point, and we see that how it will become equivalent to state feedback control, or how by choice of L and M we can actually implement a state feedback control. So this I mentioned already, that it is state of the system, and stack of multi-rate output samples is input to it. This is the input and U is the state of the system. So M is, we can see it will have the size M by M, and this bold L has the size M by N bar, and both are to be obtained, both are to be designed. And this is that N bar will is summation of all the N's, and all N's, capital N's, must be greater than all nu i's, the observability indices of different outputs, corresponding to the sampling at the rate of T0. So these are to be satisfied. Now what we are doing, that we are assuming that for the system, so basically we had system x equal to ax plus bu, y equal to cx. We are considering its discrete time counterpart. So xk plus 1 equal to phi xk plus gamma uk, and yk equal to cxk. This C and gamma are different than bold C and bold gamma which we discussed. These are the corresponding to the discrete time system for this continuous time system sampled at the rate 1 by T0. So we have this matrices characterizing its discrete time system. Now for this system sampled at the rate 1 by T0, we assume at the beginning itself that we have already designed a state feedback control, either to place its poles at desired locations by pole placement techniques, or by linear quadratic regulator design, or by any other consideration. We have the knowledge of F in this control law. The input at different sampling rates is a linear combination of states through these elements of matrix F. So we assume that F has been made available, F is available, we have designed F. And this is the statement we are making. Of course, we will prove it in the coming few slides, that this control law, which we saw a little while back, will actually really realize the gain F in the state feedback control subject to these two conditions. If bold L, bold C, this product is equal to F, and if M is equal to the product of bold L times bold gamma. And this L is to be obtained, of course, F is known, M will also be obtained, however the gamma is known, C is known. These are here. These are here. Gamma and C are here, and this is the output stack. So we have to obtain M and L. These are to be obtained. And they will be obtained from this relation, LC equal to F, and M will be obtained by L times gamma. Once L is known, then it can be done. So let us first derive these two. So what we are going to do is, we had that cxk plus 1 t0 equal to yk t0 minus gamma u kt0, and to that we are pre-multiplying all terms by L. So we have this relationship by that pre-multiplication by L, and this one we substitute in the multirate output control law. This is the multirate output control law. We assume this controller structure, and in this we substitute this one. So what will happen? This ykt0 here we have to substitute this one. So it becomes m u kt0 was there, and this l y kt0 is lc xk plus 1 t0 and l gamma u kt0. These are here. And now we bring the terms of u kt0 together. So it will become m minus l gamma, bold L into bold gamma, and this one is here. Now from this we see very interesting equivalence between this and the state feedback. State feedback was uk is equal to fxk. Now we see that uk plus 1 t0 equal to lcxk plus 1 t0 if this one is 0. If m minus l gamma is 0, then this is equal to this, and that corresponds to this. So the control law, multirate output controller, controller based on multirate samples of outputs, can correspond to state feedback control, is equivalent to state feedback control, subject to m minus l gamma being 0 and lc being equal to f. Of course, if we look at this thing, this is a dynamical equation with this as the system matrix, m as the system matrix. So in order that this controller works satisfactorily, m must be such that its eigenvalues must be within the unit circle. This system must be stable, and for that the eigenvalues of m must be within the unit circle. Then we have this. This is what we wanted to prove. So I am going back. This is what we wanted to prove. So we get that in very few small derivations, which I just now explained. We got it here. So LC equal to F is the basic design equation, and M equal to L gamma, subject to M representing a stable system. Now obviously using those equations we can we can calculate the gain of the multirate sampled output controller. So there are two situations possible. Basically we are considering the equations LC equal to F, this bold L, bold C. So first situation we are considering is that all outputs are exactly sampled such that n1 equal to nu1, the number of samples of output 1 taken during one interval t0 is exactly equal to the observability index of output 1, n2 equal to the observability index of output 2, and so on. This we are assuming, that is the first situation. N1 is nu1, N2 equal to nu2, and so on. Number of output samples are exactly equal to the minimum value, satisfying that N1 equal to observability index of output 1, N2 equal to observability index of output 2, and so on. Now, if this is the situation, then C has, as we said, that C will be invertible for n's greater than equal to new. We stated this. Ni is greater than equal to new I, and Ni equal to new I. In this situation, C will have exact equal number of rows and columns, and it will be invertible because its rank is n. So L can be computed by post multiplying F with C inverse, and we get one exact L. And once L is obtained, then M is calculated using this. Of course, before using L, we have to calculate this gamma, and we had that expression for gamma. So we are first considering the situation that number of output samples are exactly equal to the corresponding observability indices, N1 equal to new 1, L2 equal to new 2, and so on. In that case, the matrix bold C will have equal number of rows and columns, and it will have rank n, which we already stated earlier. So we can obtain inverse C, and then to obtain L, we need to multiply F by C inverse on the right. We need to post multiply F by C inverse. And once we obtain L, then we have to first calculate gamma, and then M can be obtained as L times gamma, bold L times bold gamma. We can do this computation. It is straightforward. Now, after calculating M, we need to perform a check on M. We have to see its eigenvalue, and they should be in the unit circle in the Z plane. That is the necessary condition for stability. That this result comes from the digital control subject. If somehow suppose that M doesn't have its eigenvalues within the unit circle, then we have to choose a different F, and we have to redo the whole thing till both the conditions are satisfied, that L is obtained and this M obtained like this is a stable matrix. So that is where one limitation of multirate output control is that it will realize most of the state feedback gains. Sometimes it may not, because this condition may not get satisfied. Now we come to the second situation. We assume that this N1 is sampled more times than the minimum needed. N1 is greater than the observability index new 1, N2 is greater than observability index new 2, and so on. In that case, what happens is we have more unknowns. We have, because n bar will now be greater than n, system order, and there will be more unknowns, however fewer equations. Less number of equations than unknowns means there is no unique solution, and in fact there infinitely many solutions will be possible, and that makes choice of M easy, because out of so many solutions we will have at least a few solutions which will lead to a stable M obtained through M equal to L gamma. The procedure is same. We assume some of those L's because we have more unknowns than the equations, and then we plug the values of L. We solve the remaining L's and plug the values of L into this to obtain M. We check the eigenvalues of M, and if they are not leading to stable M, if the eigenvalues are not within the unit circle, then we redesign, we re-obtain L to realize that F. Means we re-obtain LC equal to F. We solve again. So if number of output samples are larger than the number of output samples required for ensuring N1 equal to nu1, N2 equal to nu2, etc., we have freedom for selection of some of the gains L, and so it is plausible that M may be obtained having stability. It's a better situation. Now we take a little time to prove the stability of the closed loop system based on the multirate output control equation, control law. So we rewrite some equations. So first is this one. We have, of course, in place of EAT0 we are using phi 0, and for this integral we are using gamma 0, phi 0 and gamma 0. This result was shown in the early part of the first lecture before this one. So this is the discrete time equation corresponding to the sample rate 1 by tau 0, 1 by t0 for the continuous time system. We had these various equations. This is that control law, and this is the equation relating the system outputs to the system states and the inputs. And then in this we had these two relations. So these we are recalling from the preceding. Just they will be handy. Now what we do is, because here, because this Ly is there, we can substitute Ly in terms of this and this in the equation for the input, and so we get these three terms. Two of them will cancel, and what will be left is this, and of course we know that LC is F. So UK plus 1 T0 becomes minus F this. So we can write this equation here, second one, and this equation together in the vector form. So we have here, and once we have this, then what we do is we make a similarity transformations. We introduce a new variable z key t0, and these are the states of the system here, x and u, and in the new system, transformed system, we have the states x and z, in which u is equal to minus phi 0x plus z. And then with this transformation the system becomes this one, and we see a very important thing from this system, that because lower m rows, these are m rows, lower m rows are all zeros, we see that the eigenvalues of this whole system are those of this and zeros. So that is stated, I think, in the bullets here, that this system has n plus m poles. N poles are those of this phi 0 1 minus gamma 0 f, the poles of the state feedback system, and m poles are all zero, all are at the origin of the z plane. So it has n poles corresponding to the state feedback system, discretized system corresponding to the continuous time system sampled at the rate 1 by t0, and m poles which are all at the origin of the z plane. So that means that if the system is designed, the state feedback is designed so as to stabilize the system, then this overall system is also available with the closed loop. The closed loop system based on multi-rate output sampled controller will also be stable. So only condition is this. This is important result about the stability of the MROC. Now we just see one design example. So we assume this system, this is A, this is B, single input system, single output system. These are the ABC matrices, and we want to design the MROC. So before we can actually design, a few necessary things to be proved. One is that the system should be controllable and observable. This is in the controllable companion form, so controllable straight away, and observable again because this coefficient is non-zero. So the system is both controllable and observable. And also this augmented system with A, B, C and 0, one can check that rank is coming 4. So the two conditions which we stated in the preceding, both are satisfied, that the control system is observable and controllable, so state feedback can be designed, and observable, and also this is having an observability index of 4, so means that it will be possible to obtain a multi-rate output based output controller. So we choose T0. Of course, in the practical systems there will be considerations, but here in this example we arbitrarily choose T0 equal to 0.2. Essentially, we should have enough number of samples which brings out the essential characteristics of the system. So T0 should be smaller than the smallest, that decay time constant or decay time of the mode varying the fastest. So we choose T0 as 0.2, and for this one, the discretized system corresponding to this will have these eigenvalues. One within the unit circle, but two are outside the unit circle, indicating that the discrete time system corresponding to this is unstable. Of course, this will also be unstable, the continuous time system, but we are discussing its discrete time counterpart. So for T0 equal to 0.2, we get this phi 0 and gamma 0, and we were talking eigenvalues are of this phi 0. Now for this we design a state feedback based on some considerations, either through pole placement or through LQR, and we see that the eigenvalues will be here. These are all within the unit circle for these gain values. So we have u equal to fx with this f to stabilize this system. Once we obtain L, then we have to obtain C, and for that we have to choose N1, that number of samples of output in one T0, which is 0.2. So we choose N1 as same as the observability index, which is 3. And so delta will be 0.2 by 3. This N T0 by Ni. This is what delta I is. So here there is only one output, only one input. So T0 is 0.2 and N1 is 3. So delta is 0.2 by 3 second. And for this, the phi, so this is the same continuous time system which was given in the beginning. However, for the sampling rate 1 by delta. this one, and this is the input matrix corresponding to that. So these will be used to calculate that bold C, etc. So these are the relations we recall, and of course for this system it will be C1, C2 and C3 only, and there will be, here there was N1 rows, so there is only one output, so C1 e power minus A delta, C1 e power minus 2 A delta and C1 e power minus 3 A delta. Likewise this and likewise this. So we get this bold C, and then we get L by this simple computation, and that L comes as this. And this L will realize the state feedback gain F. Now once we get L, then we have to calculate M, and for that we have to first calculate bold gamma using the relationship which was given here, using this one. Of course there is only one input, so there will be 3 rows. So we calculate bold gamma, it comes like this, and then we calculate M, which is L times bold gamma, bold L times bold gamma, and this comes as 0.26, meaning that the system is stable. M represents a stable system because this is less than 1. It is in the unit circle. So now, looking at all those results, we can now say that this L which was obtained by solving L equal to F C inverse, C is bold C, L is bold L, can be accepted as the gain of the multirate output controller. And control law becomes this. This is M times UKT0 minus this is L, and this is the stack of output samples taken during T0, and they are spaced by delta, you can see. So one at T0, one has T0 plus delta, one was at T0 plus 2 delta, and so on. We can obtain this L. This L realizes the state feedback gain, and so for this system we can, without an observer, we can implement state feedback through this L and through this control. We summarize this lecture. In the MROC, the samples of output are collected several times during one sampling interval of the input. So we have a bigger sampling interval T0, in that we collect several times the samples. And then the input is computed using these samples, as we saw, for example, in this one. Input is computed based on these samples through this product, L times Y. So input is computed using the samples of output and the previous value of the input. This is the previous value of the input. And it is updated at the end of the sampling interval. So we will collect all the output samples here, and then UKT plus 1 will be applied here, which will be computed based on all these. Now, almost any state feedback gain can be realized, because we saw that sometimes for some state feedback gains, if M is not having stability, then we need to change F and we need to obtain M which will have stability. So most of the time the state feedback gain will be realized. However, sometimes it may happen that the state feedback gain may not get realized. That is why this almost. So most of the time through the MROC, the state feedback gain can be realized. And of course, observer is not required. The only necessary thing is that we will be ready to implement the controller through discretization. And of course, this is the trend now. most of the time the controller is now implemented using a computer which anyway does the discretization. So we can go for, in many industrial applications, for this kind of MROC. There is one limitation for this. This outputs are collected during a sampling interval. So the samples of output are available at the end of the sampling interval, and that is where the input can be calculated. That means for the first sample between 0 to T0, this controller cannot be implemented. This controller can be implemented subsequent to T0. So T0 to T0, etc. In this one, this can be implemented. However, not in this one. So that is a limitation, that in that situation input has to be assumed. If it is assumed 0, then for some time the system behaves as an autonomous system, and that should be acceptable. So this is one limitation of multi-rate output controller that we should keep in mind. And we should not forget that we should obtain L, and for that L the matrix M must be stable. These are two very important considerations. However, this MROC is very promising, as the trend now is implementation of controllers to microcontrollers or digital computers. It will be possible to realize any state feedback gain for the system through MROC, and an observer will not be required. Thank you very much. See you again in some other lecture.